Okay, so we did last time do a bunch of half reactions. We're going to keep doing the half reactions here, but this time we are going to start to add it up to an overall reaction. And then we're going to take an overall reaction, break it apart, and then re-add it back up. So I'm going to start by taking chromium 3 plus to dichromate. Now, remember, this is taking away all the spectator ions that aren't doing anything. So is this chromium chloride becoming, I don't know, sodium dichromate or something like that? I don't care about the counter ions that brought these guys here. I just care about the people that are doing things. So it doesn't matter where the Cr3 plus came from or where the dichromate is. We'll figure out how to build that later. Again, just stripping off the spectator ions. All right, so, in fact, I think we should actually start this in black, because we would start with those guys in black. So the first thing we need to do is we need to balance everything that is not oxygen or hydrogen. So in this case, it's chromium. Let's see, Patrick, you want to do this one, or you want to punt it over to Shauna?
Follow Shauna.
Shauna, you're up. Start balance this thing for me.
All right, there's 2 chromiums. There's 7 waters.
Okay, so right, we have now we have the 7 oxygens, so now we have to do the 7 waters. Where am I going to put those 7 waters?
On the left.
Okay. Okay.
And then 7H plus.
Hold on, you guys wanted me to do it in steps, so I forgot. Okay, and then I'm sorry. Go ahead, Chef.
Then 14 H pluses.
On the
right.
Okay. So again, 7 H2Os are on the left. 2 chromium 3 pluses. Goes to make the dichromate. And now 14 H pluses. All right, so what's the charge on the left?
6 plus.
On the right?
14 plus. 12 plus.
There you go. You're right, 12 plus. Now again, this is the part that will get people, is you got to look at the entire side and just be very careful. So now we got 7 H2Os. We got the 2 chromium 3 pluses. We got the Cr2O7 with the 2 minuses. The 14 H pluses. And
6 electrons.
6 electrons. So now we're +6 on both sides. Is this oxidation or reduction?
Oxidation.
Oxidation, because we're spitting them off on the product side. Reduction, we'd be gaining them on the left. So this is an oxidation. Okay. We have a sulfur going to become sulfide. Kimchi, balance this. First, we balance our sulfurs. Are we good?
Yeah.
Okay. Then we look for any oxygens and balance those with waters. Are we good?
Yeah.
Then we look for hydrogens. Are we good?
Yeah.
And then we look for charge. Are we good?
No.
Okay. So what do we have to do?
Put 2 electrons on
I think you said 2 electrons on the left. You must be pretty far from your computer. Or maybe I have to turn me up. Oh, you are? Okay. All right, so sometimes it's that easy. Just want to point out, sometimes you don't have to do every single step. Well, you are, it's already done for you. Is this oxidation or reduction?
I have a question.
Yeah.
For the chromium, why is it that you add H2O instead of just regular oxygen?
Because, well, so good question. These are all in watery environments. And as we will see when we start looking at the different electrodes, that the water will actually end up playing a part. I'm surprised you haven't asked, like, what about the H pluses? Mostly we get the H pluses because in our watery environments, they come because we use an acid as the electrolyte for the solution in general. But I don't know if that answered your question.
It does. I was a little bit confused. I was like, wait, what if there's no hydrogen? You just add water, magically appears?
Well, remember the hydrogens are there to counterbalance the fact that the water is going to be involved to balance out the oxygens.
Okay.
Notice that our sulfur down there, at least its half reaction, doesn't seem to need anything except for the electrons, right? So, and this is where it gets kind of interesting because clearly if I'm going to put these two things together, which I will, because this is a reduction, if I put these two together, the sulfur will be in a watery environment. It will be in an acidic environment. It's just that it doesn't require those two components for its own changing, but the chromium does.
Okay.
So now what we want to do is let's add these guys up. Add them up for the overall reaction. Cancel electrons. And this is where we were talking about making sure that we multiply one or something in order to make sure that we have all of our electrons being transferred and none of them hanging out in thin air. So hopefully you can see that we have 6 electrons in the oxidation. We have 2 in the reduction. So these won't add straight away. What we're going to have to do is multiply the reduction here, the sulfur, by 3 in order to make this work. So I'm going to go ahead and nix the colors here for a minute. Well, no, I guess I'll keep the colors. So we're going to take 7 H2Os plus 2 chromium 3 pluses, Cr2O7 with a 2 minus, and the 14H pluses, and the 6 electrons for that one. And now we're going to take the reduction here and put that to add up. So 2 electrons plus the sulfur, going to make a sulfide. And I will say we have to take and multiply this one by 3. So that the 6 electrons here will cancel. In the overall reaction then, what we're going to see as we add these up is that we end up with 7 waters plus 2 chromium 3 pluses plus 3 sulfurs. We're going to make 3 sulfides, dichromate, and 14H pluses. Now in this, 6 electrons were transferred. So for every 2 chromium 3 pluses, we needed 3 sulfurs to match them to shuttle and take those electrons and complete this redox reaction. And again, we are taking out the rest of the spectator ions. We don't know what's bringing the H plus there. We don't know what's bringing the sulfides. We don't know what's bringing the dichromates. But their spectator ion is what's doing that. Okay, let's do another one. Here, I'm going to give you the reaction as it stands. We're going to break it apart and then re-put it back together with all of the H's and waters and their multiplicities in there. So you might have something that looks like some iodine and some chromate are going to make some chromium 3 pluses. And that triiodide. This is a classic one. Chromium is used a lot for these types of things because it does some really cool chemistries. So it's not surprising that we have this one. And iodine is a wonderful electron shuttle in either the triiodide or the iodate form. So what we want to do here is we want to break this up into its 2 half reactions, balance those half reactions, and then bring them back together. So we're going to break these out into their half reactions. Balance them. Put them back together. So the first one I'm going to do is I'm going to break out my iodide. So I'm going to have my I minus, going to make I3 minus. Steps or just colors? I'm okay either way.
Colors.
Say again?
Colors.
Just colors? All right. So since we're just going to go with colors, we see that we have 1 iodine on the left. No, wait, does that? 1 iodine on the left, 3 on the right. So I'll put 3 iodines here. I'll look for oxygens, okay. Hydrogens, okay. Charge, I notice I have a 3 minus on one side and a 1 minus on the right. So I'm going to add in my 2 electrons there. Next, I'm going to have my chromate. So I'll have my CrO4 with a 2 minus. Going to become Cr with a 3 plus. Just taking this guy right up here. That's our second one. We have 1 chromium on the left and 1 on the right. We're done. We have 4 oxygens on the left. So we'll add 4 waters on the right. That now put 8 hydrogens on the right. So we'll put 8 hydrogens on the left. And then I'm going to go back to Chef. Chef, what is the charge on the right?
Looks like 6 plus. I'm sorry, on the left is 6 plus, on the right is 3 plus.
Okay, good. So then what do I have to do?
I need 3 electrons on the left.
That is correct. Okay, if I'm to add these two together, clearly my electrons do not cancel. And so hopefully you guys see that all I have to do there is multiply the bottom one by 2 and the top one by 3. And that'll make my 6 electrons cancel on both sides. All right, so if I do that, let's see, what do I get here? It looks like 9I minus plus 2CrO4 2 minuses plus 16H plus goes to make 3 triiodides, 2 chromium 3 pluses, and what is it, 8 waters? And so now we see the fuller picture. At the top there, we had 2 systems, iodide going to triiodide, chromate going to chromium 3 plus. Those cannot do what they're trying to do straight away. Your first clue is the fact that at the top, we have a -3 on the left and a +2 on the right. Something here has not been accounted for. And that's where our other pieces, the waters and the H pluses, are going to come through. They're going to balance out partially for charge. They're also going to make it to where when we have to multiply these guys together to make sure that all the electrons are transferred, that we have the correct number. And so at the end, we see that there were 6 electrons transferred. It just took 2 dichromates and 9 iodides to do it. Okay. Now, I'm going to do another one. We doing okay? All right, this one is going to be manganese plus hypochlorite goes to make manganese hydroxide and chloride. Ben, do you notice anything? Oh, I'm just kidding, Ben. Anybody notice anything funny about this one? Basically, it's the same. Basically, base.
The OH?
There we go. Yeah, we have OHs this time. So what does that mean? Can we do this in an acid? Nope. So this is where we're going to do this in a base. So the OHs are going to say, there's no point in having H pluses in there, it would kill what we're doing. So this one has to be done. In a base. And it's because everything right there with the OHs. So let's go ahead and break this apart into its 2 pieces. We have our manganese going to be manganese hydroxide. Use 2 hydroxide. We do everything exactly the same with the acid, and then we're going to convert it all to the base. So once again, balancing everything that is not hydrogen and oxygen, check. Manganese are fine. We see that we have 2 oxygens on the right, so we're going to put 2 waters on the left. Then we have to balance out our hydrogens. We see that we have, let's see, four hydrogens on the left and only 2 on the right. So we're going to have to add 2 hydrogens on the right. We have 0 charge on the left, and we have a +2 on the right. So there's the 2 electrons. Now, so far, this is the same balancing we've done. All we have to do now is shift everything to a base. To do that, we're just going to add hydroxides to both sides to cancel out the H pluses and combine them to make water, and then cancel out any waters that appear on either side. So what we're going to do here is we're going to add 2 OHs to both sides. These 2 guys are going to become a couple of waters. And so I'm going to go ahead and rewrite this as, let's see, I'm going to go ahead and add that up to have 2 OH minuses plus 2 H2Os plus a manganese, going to make manganese hydroxide. Now we have 2 waters. And we still have our 2 electrons. Our 2 waters cancel each other out left and right. And at the end of everything, we're left with 2 hydroxides plus some manganese. Going to make manganese hydroxide and 2 electrons. Is everyone okay?
I have a question.
Rio, you okay?
Forrest.
Kimchi from way back.
Sorry, I'll try to move closer. Why did we have to like go through all that when we were really just gonna add 2 OHs?
Because, and it may become more apparent here in just a moment, not all situations will just throw OHs. You may find that you don't cancel out all your waters as conveniently as we just did here. And so you do have to go through the whole acidic version first. You can't just like sort of skip to the end. So, I mean, a trivial example always goes like, oh, well, you're just doing this instead. And that's not always the case. So if you ended up just going like, oh, we're just going to throw the OHs over there, it would get into problems in other problems where the waters don't always just cancel out on both sides. This one just happens to do it. This guy here is an oxidation. We lost him. Our other one that we had was the ClO minus going to Cl minus. Then we have ClO minus going to Cl minus. Balance everything. It's not hydrogen and oxygen. Check. Now let's balance it to with our waters. So now we have to add 1 water on the right, which means we have to add 2 hydrogens on the left. We have a charge of +1 on the right and -1 on the left. So we have to add now 2 electrons on this side. But since the manganese hydroxide was in the base, this one also has to be in a base. By the way, hypochlorite is a base. Sodium hypochlorite is bleach. So it makes sense that we'd be doing this in some sort of basic solution. So we're gonna have to add a couple of OHs here and a couple of OHs on that side. So now we have 2 electrons plus 2 H2Os plus a ClO minus, going to Cl minus, plus an H2O, plus 2 OH minuses, and Kimchi, hopefully this answered your question. And our one above, the waters canceled out, and so it looks like we were just balancing everything with the OHs to OHs, and we can't do that here because now only one of those waters goes away. So we get rid of one of those, and that one goes away. We now have 2 electrons plus a water. Plus a ClO minus. Those make Cl minus. And 2 OH minuses. And this is a reduction. We're gaining those electrons. So did that sort of show you that you can't just do the OHs, Kimchi? Yeah. So now let's go ahead and add these 2 together to figure out what the nominal thing of just manganese and hypochlorites and all that, what does it really entail? We still have to have an electrolyte in there, this time the base, so add them up.
Okay, just double checking. You knew to add 2 hydroxides because you had 2 H pluses?
Yes, yes. And these 2 things right here, that's what's going to combine to give you the waters. You gotta get rid of them. So we have 2 hydroxides and a manganese. Going to make manganese hydroxide, 2 electrons. Water plus a ClO minus. Going to make a Cl minus and 2 OH minuses. And this is where something even crazier shows up. Because right now, we don't have to do anything with those 2 equations. The electrons cancel. But look what else cancels. Yeah. So if we see that, two electrons cancel, but also the two OH minuses. And so at the end of the day, you have water plus manganese plus ClO minus going to make the manganese hydroxide and a Cl minus. Curiously, this just happens in water. So at the end of the day, it's funny. We go through all that rigmarole, which we need to, because if this system were slightly different, we might need those hydroxides in there. But it turns out that the hydroxides just from the water itself is enough to make this reaction start to do what it wants to do. That's kind of cool. Give me just a moment, guys. Sorry about that, guys. I don't know how much of that you could hear, but it was enough to make it difficult for me to concentrate. Oh, wait till they're 3. Good stuff. Okay. So balancing, adding them up. You guys okay? I hope so, because I can't make these things up. This is actually one of those rare times where I was watching a colleague way back in the day, and they were doing these reactions, and someone's like, I need another example. So he's like, all right. And he just like threw one up there. And about halfway through, I could watch his face just turn to alabaster. It was amazing because he put one up that couldn't be balanced. And I was like, oh, mental note, never just make up a redox reaction. You can get yourself into trouble. So if we need more after lecture and some other time, I can dig some up and we can balance through them. There's plenty in your book, I think, too. But you guys are okay, right? Just lie to me. Just say yes.
Yes.
Thank you. All right. We spent a little bit of time doing all these balancing the reactions because now we're actually going to try to actually build an electrochemical cell so that we could make this thing work. So building electrochemical cells. So now we're going to go ahead and make these for realsies. All right, what you're going to do, start with the half reactions. So you're going to be given some sort of redox reaction. You have to break it apart into the half reactions. Once you do that, everything that is in your half reaction must be in its half of the cell. Everything in that half reaction must show up in its half of the cell. And interestingly enough, if there's a metal that's present, use it as the electrode. If a metal is present, use it as the electrode. Otherwise, use carbon or platinum. You can use those two because they will conduct the current. They will let the electrons flow. but they're incredibly unreactive with just about everything, so they will actually end up not taking part in the reaction, even though they happen to be there. Very inert. Okay, so you're gonna start by breaking apart everything into the half reactions, making sure everything shows up. And if a metal's there, use it. If not, platinum or carbon. So let's go back to our original favorite. Go back to our first love. Zinc plus copper 2 plus. Let's make copper. And zinc 2 plus. That's the one we started with. So let's start there again. Let's go ahead and build this cell. It's probably one of the most common and most famous cells. We've actually known about this from antiquity. There's evidence that even the ancient Egyptians had some sort of working battery of this type. It's kind of cool. Don't know what they did with it, but they had it. So let's break it apart. So we got zinc becoming zinc 2 plus. Let's see, zinc is balanced, oxygen is balanced, hydrogen is balanced. Now it's just balance the charge. 0 on the right, plus 2 on the left. So we need to put 2 electrons on the right to balance it out. Boudica, oxidation or reduction? That's right, oxidation. We lost the electron. Do the other one, copper 2 plus, going to become copper. Hopefully it's not too much to see that it's going to be almost exactly the opposite. And that's going to be the reduction. So let's go ahead and make an electrochemical cell, one of those nice little H cells as we would call them. And let's take a look at each of those half reactions and put their pieces where they need to be. So I'm going to go ahead and draw one of these. Okay, I'm going to go ahead and put the oxidation on the left. I don't know. So over here, I'm going to put the oxidation just because. I'll put the reduction on the right. In the oxidation side, what are the pieces that we need? Harvey.
The zinc 2 plus, and the 2 electrons.
Okay, so the 2 electrons will be the thing flowing outside of the cell, and there's no real way of adding electrons. So at the end of the day, we're okay with not having that as an ingredient. Now, since you did mention the zinc, actually, I'm going to go ahead and color code this a little bit here. We'll just do that. Do that. So on this, since we had zinc metal, we can go ahead and use that as the electrode. But I forgot to put my little semi-permeable membrane here. There we go. And then putting the zinc ions into solution, we can do that any multitudes of ways. Can you think of anything that would be soluble that we could put in there for getting us zinc 2 pluses? That was still to you, Harvey. Can you think of a soluble compound with zinc that would dissolve out?
Sorry, a truck just went by. What was the first part?
How can we get zinc 2 pluses in solution? Give me a compound that would dissolve to give us those zincs.
think of it on my head.
Okay, that's fine. A common one that could be used would be zinc sulfate, because sulfate is sort of like sodium. It sort of sounds the same. Sodium swims and sulfate swims. You could have also used zinc chloride. In general, even though all nitrates are soluble, you want to stay away from nitrate unless you absolutely have to, because nitrate tends to do its own reactions off to the side. So you want to avoid that if you can. Sulfates are usually safe, and the occasional chloride is also good. Okay, so Patrick, on the reduction side, what are our pieces?
It's gonna be Du2 plus and Cu.
Okay, so since we have a solid copper, we should be able to use that as the electrode. And then, is there anything you can think of that we can use to get copper in there?
CuSO4.
Yeah, absolutely. You know, in a lot of these, if you can keep that counter ion the same on both sides, you absolutely want to do that. The simpler you can make this system, the better. So at the top, we're going to go ahead and connect these two with the wire and let them see each other. We know that the zinc, as soon as that happens, is going to start spitting off zinc 2 pluses. We know that the copper 2 pluses are going to be racing up there onto the copper and depositing. As this occurs, the electrons are flowing from the zinc to the copper, which means that the negatives are going to the right. We have to have some negatives going across the membrane, and our good old friend sulfate will be the counter ion to go across. All right. CPR, cathode positive reduction, a negative electrode. And there we have it. Any questions on how we built that cell?
How did you decide which one was the anode and the cathode?
Oh, remember our acronym, oops, was CPR. That is cathode positive reduction. And so that's the easiest one for me to always remember. If you note that the electrons are running away from the zinc, electrons are negative, so the zinc must have been a negative electrode. So you could say a negative electrode or anode for the zinc. But it's usually easier to identify the cathode side and then just know that the other one's the anode.
Will the cathode side always, like, the Cu2 plus is going into the Cu? Is that always going to be the cathode side?
I don't understand or like that question. I'm not quite sure what you mean.
I don't really know what's going on. The copper 2 plus is like being.
It's racing up. It suddenly sees electrons crowding on the surface of that copper. And when it does that, remember this goes back to the activity series. You weren't here for my 110 or my 120 when we talked about these, but the activity series of metals is where you have a hierarchy of who is more reactive than whom of the metals. And the more reactive you are, the more you're going to want to do what you do. And that is zinc wants to lose its electrons and become zinc 2 plus. And it likes to do that a whole lot more than copper likes to. So if you let them see each other, zinc is going to try to find a way to dump off its electrons to the copper and say, I'm going to go do my thing. Here, you take these. Now, in that, if you just sort of stuck them next to each other with no way to conduct the current and make the circuit, basically nothing's going to happen. But if you do actually have them in an environment where they can start to have some sort of other thing in here, some other thing to shuttle up the charge as they dump electrons and gain electrons, then you're gonna see the reaction going. What we're doing is we're absolutely creating the perfect environment for this to do exactly what it wants to do. For anybody who's in an old enough house like me, I have both iron pipes and copper pipes. I cannot let those two pipes see one another. So when I have to join up a lead pipe, an iron pipe to a copper pipe, I actually have to physically separate them with something called a dielectric junction, or why am I forgetting the actual name? Anyway, what it does is it separates them physically from each other so they cannot touch, so they cannot do those electron transfers, because in the old days, they used to just like, oh, I'll just bolt them together, big deal. And then basically it would, the iron would, over time, slowly just dissolve away and your pipes would burst.
Mm-hmm.
So you had to actually physically separate them. If you didn't want this to happen at all, you just go like this, boom, nothing's gonna happen. And this is exactly what's happening in your batteries for your stuff, is that until you need it, you don't complete that circuit. And then you hook it up, you turn on the switch, and bam, they can see it, and they start doing their reaction, shuttling those electrons through everything, and then you get the power as it goes through your device.
Right.
As the electrons race over to the copper, those copper 2+ are like, hey, those are mighty tasty. And so they actually migrate their way to the copper, but as soon as they grab those electrons, they're no longer ions. They're no longer floating around, and they just start clumping up on the surface of the copper. We don't really think about it, but actually, there might be some people in here who have ever ripped open a battery, and I'm looking at you, Ben, because it seems like something you would have done in your reckless youth.
Absolutely.
Have you actually opened up a car battery and looked at what's inside?
Yeah, the acid or the whatever electrolyte burned a piece of my ear off.
What did those plates look like inside? Those lead plates, were they nice and pretty and perfect?
No, they looked all spotty and I don't know, like they were
Yeah.
like they were
And
being
we're going to talk about that as we go on. They start out really pretty and pristine and nice, but as they keep getting used and these ions pop on and off and do their stuff, they're either going to look really pitted or really bumpy, because they're either becoming ions and chipping away, or they're just like clumping up on the surface. So when we get to the car battery thing, I'm going to come back to it and sort of touch on this once again for you, Kimchi. But essentially, as long as you have a solution, as long as you have the ions, this thing's going to work. As long as you have the electrode, this thing is going to work. But you can clearly see that zinc continually spitting off its zinc 2+ over here, eventually is just going to wear away. It's going to have nothing of itself left. On the copper side, it's just going to keep pulling those Cu2+ in out of solution and clumping up around the copper, and eventually you're going to run out of the copper 2+. You have a dead battery at that point.
Yeah. No, I think I get that. It was just more like I didn't really. You explained it.
Okay. All good.
Yeah.
All right. Now we are doing this 1 molar solution. Can anyone guess why we're doing that?
Because conditions.
That's right, standard conditions, right? The 1 molar is because we wanted to stay at standard conditions. 1 molar to be at standard conditions. And the reason is because what I can do is I can go to the reduction table. Now what this is it's a list of reduction reactions at standard conditions and the voltage you would see. And so if I do that, I get zinc 2 plus 2 electrons, goes to make zinc. This has an E naught equal to negative 0.7618 volts. I can look it up for copper. Copper 2 plus 2 electrons, going to make copper. That E naught is positive 0.3419 volts. So I'm just going to go look those things up. People have done the studies on them. They say, okay, this is what we have. Now, what do those voltages tell you, though? Look at the zinc one. What does that negative voltage tell you?
Is it?
I was
Say
gonna
again?
say spontaneous.
It's not spontaneous as written, right? So the negative voltage for zinc says it is not spontaneous as written. Which means what would it rather do?
Go the other way.
That's right, it would rather go the other way. So, and the positive voltage for copper says it is spontaneous. As written. Now, what we're going to do is we're going to see that if we made this electrochemical cell as we have it, what kind of voltage do you think we should actually see if we put a voltmeter on here and said, okay, well, how much power are you actually giving me? What's the voltage there? Well, in order to do that, we need these half reactions as we see them to add up to the overall reaction that we see above, which we've broken apart. And hopefully you can see that my zinc reaction is backward from what I need it to be, right? Down here, the reduction table is listing it as the zinc gaining the electrons. We need it written as the zinc losing the electrons. So let's see if intuition serves. So to add them up, we need these reactions and their voltages. To add up. So we're going to have to reverse the zinc. So we're going to go zinc. Going to become zinc 2 plus 2 electrons. If we flip the reaction, what do we do to the sign?
Flip the sign.
Flip the sign. So that's now positive 0.7618. The copper was just fine. That E naught was a positive 0.3419. And if we add all these up, we see the electrons going away. We're back to zinc, copper 2 plus, goes to make copper, and zinc 2 plus. And if we add the reactions, of course, what are we going to do to the voltages? We're going to add them up. And that'll be a positive 1.1037 volts. Okay. You guys all right? Flip reaction. Flip the sign. Now this is actually a pretty standard battery situation. This has been known and studied for a long time. If you were to actually go in and do this, you would get this voltage. In fact, we were supposed to do that, but we're in quarantine. Let's do another one here. Let's do iron 2 plus silver plus goes to make Fe 3 plus silver. All right. First things first, let's break it apart into the two reactions. So we have Fe2 plus going to Fe3 plus. And again, we're going to start out slowly building up our abilities. So we've already balanced the irons. There's no oxygens, no hydrogens. We just have to balance the charge. So we just add one electron. On the silver side, we have the Ag plus. And of course, just one electron is needed there. So here we have the oxidation. Here we have the reduction. I feel like I'm writing a little fast, guys. Are we okay? Isa? Just making sure. You're okay, Isa?
Yeah, we're good.
Okay. Go ahead and build our cell here. Okay, let's see. Low band, I didn't realize you were here.
I got here a little late.
Okay, did you watch the last video?
The recorded one on Friday.
Mm-hmm.
I actually did not get to do that. I didn't see
I can't
because
call
my
you.
email isn't set up and it keeps going out on me.
That's all right. I was just gonna call on you, but there's no point.
I don't know.
Isa, let's go with you.
What's up?
I guess let's just start oxidation on the left. It doesn't really matter.
Okay.
If I think about it, I'm going to try to make one of these. Actually, let's go ahead and do this one backward, just because. quote backward. It doesn't matter which way you go.
Okay.
I really want to do one where it's easy for us to see, but I don't want us to get into the habit. I mean, I get into the habit because eventually, if you guys remember me from Chem 110, I would always make my precipitate the second thing on double replacements. It's just how it falls out in my brain. But I don't want us to get caught in a convention where if we build this quote the opposite way, that we don't start on the wrong side, because we're gonna do something at the very end of this whole thing to write out what this would look like in a textbook of all things. Okay, so on the reductant side, what are our ingredients?
Your silver, Ag.
And the silver plus, right?
Yeah.
Okay, so since we have solid silver, we can use that as the electrode. And now, what might I use to make silver go floating around?
1 mole of silver's sulfate.
Actually, this is the unfortunate time that we have to use nitrate, because that's basically the only thing that's going to get silver into solution.
Okay.
This is the unfortunate, you have to use the nitrate because all nitrates are soluble, and on your solubility table, that silver comes before the chlorides or anything else that might work for it. So nitrate's going to be our person on this side.
Using nitrate because the charge balances.
No, I'm using nitrate because it's the only thing that'll get it into solution. Silver sulfate's not soluble.
Yeah.
Okay, so Isa, on the right side, what are our pieces?
Iron, iron 2 plus.
Not iron. Iron 2 plus and
Oh, iron 3 plus. My bad.
so do we have the physical metal in the half cell?
No.
No. So in the case where we don't have that physical metal, we have to substitute. What do you want to use as the substitute here?
I'm not sure.
We can either use platinum or we can use carbon.
Let's go with carbon.
You want to go with carbon? All right,
Yeah.
so I'll do this platinum or carbon. I'll just put it there so that some people are like, oh, I want a carbon electrode. It's fine. I personally go with platinum here just because I like metals with metals and non-metals with non-metals, but it would work. Okay, so now, can you think of a compound that would get us iron 2s in solution?
I'm going to look at my solubility table.
That's fine. In the meantime, I'll go back to the other workhorses. You could have gone sulfate. That's totally fine. I like chlorides. It really doesn't matter as long as you can get something that looks soluble. You'll be fine. Okay. So now that we have that, let's go ahead and hook them up. Let's figure out which way the electrons are going. Which way are they going here, Isa? To the right or to the left?
To the right. Wait, no, to the left.
Of course they're going to the left because I was making you have to start thinking here. And again, I will probably go back to the convention of oxidation on the left, reduction on the right. I'm doing this such that if you decided to build this in a certain way, you just have to be very methodical and watch what's happening, and you won't get tripped up.
Right.
So, yes. So since the electrons here are getting spit off from the iron side, and they're going toward the silver side, which means if the electrons are going to the left, then who is going to the right here? That nitrate. The only negative thing on that side has to be going there. Which means, you know, we're looking at silver ions racing up. And then there's no good way of showing this, but what would end up happening is that an iron 2 would run up. I guess I could do it like this. This is going to be fun. Just go ahead and see if I can move that down. What this would look like is that you would have an iron 2 plus running up, and on the back end becoming an iron 3 plus. So as it runs up here and it touches the electrode, it gives off its electron and just becomes an iron 3 plus at the bottom, or on the back end. So it actually, this time, kimchi, nothing's sticking on there. You're still going to run out of your stuff, but it's not going to stick anywhere.
But the electrons are coming from the side with the iron anode.
Yes. So that is correct. This is the anode, which means the other side is the cathode. And again, that silver plus is being reduced down to silver. So that's the reduction side.
Is anode always on the side with the reducing agent, I guess?
I'm not gonna.
I don't know if you talked about that or not.
I don't. Okay, so that's something that I'm just going to leave out. Well, I'm going to say it, and I'm not going to ask you about it because if you're, if you are the oxidized, that means you are a reducing agent. If you're being reduced, that means you're an oxidizing agent. It's really weird that we have essentially opposite names for things doing the same thing. So I'm just going to ask if it's the oxidation or the reduction reaction, but I'm not going to ask you to identify the oxidizing agent type thing. And I know you have previous knowledge of that from somewhere else, but this stuff is hard enough as it is without getting tripped up on, is it flammable or inflammable? Yes, you know, I don't want to confuse or muddy the waters. If I go to the literature, I would find that iron 3 being reduced down to iron 2. The E naught for that is 0.771 volts. And if I look at silver being reduced, its E naught is 0.7996 volts. Now, again, these are reduction tables. These are reduction reactions. We had to have a convention. And we said we're going to write everything as gaining electrons. That's it. If you need it the other way, flip it around. But we had to have a convention. So we do have to flip the iron around. So we have to flip the iron equation. So here we have iron 2 plus, going to be Fe3 plus an electron. So that means that E naught is now negative 0.771 volts. We still have our silver plus an electron goes to make solid silver. The E naught there is 0.7996 volts. Add that up, we get our equation of Fe2 plus the silvers. Silver ion is going to make solid silver and Fe3 plus. And it does it. is still positive, 0.0286 volts. It is spontaneous. Okay. I think we'll do just a couple more things here. And then we'll call it. We everyone okay? Love silence. I'm glad you asked, Ben. How are all of these voltages defined? These are all going to be off of something called the standard hydrogen electrode, often abbreviated as SHE. It was the weirdest thing when I started doing my electrochemical work in grad school on lithium batteries. I kept seeing in the literature before I understood what was going on. They're like, and then she, and I was like, who is this she and why is she capitalized? And it took me a while to realize they were doing the abbreviation for the standard hydrogen electrode. It's kind of an embarrassing little story there, but there you have it. So what this is an electrode you can make comparing hydrogen gaining electrons to make hydrogen gas. And this is how it sort of looks. Let's see if I can build this here. This is going to be interesting because I can't erase, so I gotta be very careful. Now I'll just put a little porous stone there. Then we'll come up, and then we're going to build another cup. Oops. And build another cup over here. And we have to make them see each other. And so we're going to make a salt bridge. Okay, I'm going to pick zinc because it's a classic one to do here. What's going to happen is on the left-hand side, we are going to have 2 H pluses plus 2 electrons, a reduction, going to make H2. So it's going to be gaining electrons. On the other side, we're going to have zinc going ahead and doing its thing and making zinc 2 pluses and spitting off those self-same 2 electrons. Now, hopefully it doesn't take too much imagination. We already have it here. There's nothing else we need on the zinc side except for the metal and its solution. So we just sort of saw that before. So we can use zinc as the electrode here. And we can have 1 molar zinc sulfate inside of it. Now I've drawn something very strange right here on the left-hand side, because if we are going to compare it with hydrogen ions now going and making hydrogen gas, what's going to be our electrode? And how do we get hydrogen gas in there in the first place? So what they do is they take 1 atmosphere of hydrogen gas and they pump it into the bottom of a cell, and at the same time, they're going to take this guy right here, and this is going to be a platinum mesh. So the hydrogen is going to come in, it's going to bubble up, and it's going to hit the mesh. We also need the hydrogen ions in there, so we'll do a 1 molar HCl solution in there. That will get us our ions, and that will get us our hydrogen gas. So we have both of those pieces. And we're going to take, and we're going to connect those two. Now, this guy right here, this is defined to be (0 volts). If I do this reaction as we see it, and I hook a little voltmeter up here so I can measure the voltage that's going across there. So I'm going to put a little voltmeter right there. I would see that on the other side, this would give me a positive 0.7618 volts. Now, this is why, but since the zinc is oxidizing, right? We flip it, and that zinc 2 plus 2 electrons going to make zinc. That's why we have that E naught is equal to a negative 0.7618 volts. Now, this standard hydrogen electrode, this is exactly what they would do for each and every one of these metals that you wanted to figure out what was going on with them. What is their driving force? What is their thermodynamics? They would take a hydrochloric acid solution. They would bubble a bunch of hydrogen gas through there at atmospheric pressure. Those bubbles would run up, hit that mesh, do their thing, and they'd put someone else on the other side to try to either give or take those electrons. Now, if instead of dumping off the electrons over to the hydrogen, if it tried to go backward, of course, that initial voltage would be negative, which means when they reduced it, it would be a positive. But they did, this is how they basically built what are called reduction tables, is they would do these reactions against this, what is called the standard hydrogen electrode. I want to point out a couple things about it. Standard conditions, we had to have the 1 molar HCl and the 1 atmosphere of pressure, also to get the standard conditions. But since ESA was actually going and getting her little solubility chart, or yeah, it was your solubility chart, right?
Yeah, what about it?
Yeah. Well, the other chart that you might have had also in your notes somewhere was the activity series of the metals.
I believe so.
Yeah. And if you go back to that activity series of metals, all the way back to the Chem 110, we put all the groups 1 and 2s up at the top. Then we had a whole bunch of transition metals in the middle. And then we had hydrogen in parentheses, followed by all the noble metals, those that would not react. This is the reason why. Because they always compared it against, would it react with HCl? Would it react against the standard hydrogen electrode? All the others would have yielded a positive voltage. The other ones did not. So once they made this benchmark for comparison, all sorts of cool stuff fell out. So how do we get these voltages in a redox reaction? We've already looked at adding them up, but we got to recall how they're tied into Gibbs. So how do we really get these voltages in a redox reaction? You almost add them up. Almost. So far we have, but it's been coincidence. Let me show you. Do a little recollection. Delta H, delta G. When you add reactions up to get the overall reaction, you also add those values. When you add these reactions up, you also just add the delta H or delta G. But delta G is equal to negative NFE. So this is where it gets interesting. This guy right here. We have to take into account the electrons that are transferred, right? This was a scaling factor to go from an extensive to an intensive property. So we are still going to add them up. We just have to keep track of the electrons. We're still going to add them up. But we just have to keep track of the electrons. So I'm going to go back to the ones we just did, the copper and zinc and the iron, and we'll do one other, and then probably call it a day. So let's go back to this guy. Go back to the copper 2+. Plus 2 electrons goes to make copper. Followed by the zinc, going to be zinc 2+ plus 2 electrons. If we add these up, we get copper 2+ plus the zinc goes to make zinc 2+ and copper. We've been doing this all day. Nothing surprising there. But what I want to do now is I want to look at this in terms of the Gibbs free energy and then what that does with the voltages. So the first one has its own Gibbs free energy, and the second one has its free energy, which means the overall, when you add them up, has its own free energy. Can we agree on that? And Kim, she says yes.
Yes.
Okay. Okay. So what we've just done is we've said that delta G3 is equal to delta G1 plus delta G2. But that means that we have negative N3 Fe3 is equal to negative N1 Fe1 plus negative N2 Fe2. Now notice I didn't put a subscript on the Faraday's because it's just a constant. Each one of these reactions is going to transfer its number of electrons and have its own voltage, but the Faraday's are going to go away. In fact, the negatives are all going to go away. And so at the end of it, you find that you have N3E3 is equal to N1E1 plus N2E2. And so that final voltage that you should have should be the number of electrons transferred times its voltage plus the other one's number of electrons transferred plus times its voltage, all divided by the total number that were transferred overall. And of course, this can all be at standard conditions. Also have the E naught equals N1 E1 naught plus N2 E2 naught all over N3. Now here's where what we were doing very sophomorically and very cavalierly, it worked out, but check this. So for this example, the voltage that we'd have would be the 2 electrons times the voltage that we had for the, let's see, who did I put first here? The copper. If we go back in our notes, I'm not going to scroll that far, was 0.3419 volts. The zinc was transferring 2 electrons, and it had the voltage of 0.7618 volts. And overall, there were still 2 electrons transferred. And so at the end, we saw 1.1037 volts. That's what we actually were doing. We just didn't worry about it because everyone had 2 electrons being transferred at all times. Okay, I always start off with this with the duh example. So what happens in this situation? We sort of had it over there, but I'm going to take it one step further. So watch this. I'm going to have iron 3 plus an electron going to make iron 2 plus. And let me just go ahead and move that over. This has an E naught value equal to 0.77 volts. I also have iron 2 plus 2 electrons going to make solid iron with an E naught of negative 0.44 volts. If I add them up, I'll see iron 3 plus 3 electrons depositing out as straight up iron. If we were to just add this up, we'd say it's a positive 0.33 volts. Nope. And why not? Because we have a despairing number of electrons. We don't have the same number of electrons being transferred in all of the reactions. So really what this is we have the third voltage. So right here, the third one right here. So we're going to be looking at this guy is equal to N1 E1 naught plus N2 E2 naught all over the number of electrons transferred at the end. So in the first reaction, we have one electron being transferred at a voltage of 0.77 volts. In the second one, we have two electrons being transferred at negative 0.44 volts. And in the third reaction, we have three electrons being transferred overall. When the electrons are not canceling out, we have to use this. And at the end of the day, we would not be given that it would be positive 0.33 volts and would love to happen. In fact, we find out it's negative 0.036 volts. Not going to happen. In fact, what you would see is that iron would rather start spinning off its electrons somewhere and floating around in solution. Slowly dissolving. That's what it would like to do. So when electrons don't balance out, when they don't cancel out, you got to be careful. Okay,
on how neuroscience affects
let's see. How about we do
disorders,
one last one
but I don't know if you're interested if you wanted to watch that.
and then call it a day. But hopefully you see that that was actually kind of cool, being able to relate now those delta G's to the E's. The scaling factor, the electrons being transferred, they matter. We're seeing all these things coming together. And we'll see one more coming together here, not today, but what is today, Tuesday? Thursday? Okay. So we'll do a little copper plus MnO2 goes to make solid manganese and some copper ions. Let's break it apart into its pieces. So we have copper. Going to become copper 2 plus 2 electrons. The one we have is the MnO2 becoming manganese. Manganese are balanced. I'm going to have to put 2 H2Os on the right, which means I'm going to have to put 4 H pluses on the left, which means I now need 4 electrons on the left. Now, as I look at this, and I add it up, and I look at their voltages, a couple things we have to do. If I'm going to add them up, this guy has to be multiplied by 2. get my electrons to cancel. So at the end of the day, I'll have 2 coppers plus the manganese O2 plus 4 H pluses goes to make a couple of copper ions plus the manganese plus 2 H2Os. Now, I go to look up these voltages, and I want to point out that this guy here is an E naught of equal to negative 0.34 volts. E naught for the next one below is positive 0.0195 volts. How many electrons are transferred in the top equation?
Two.
4. The original was 2, but we had to have 2 of them there, so we are transferring 4 at the top one. Clearly, we're transferring 4 at the bottom one. How many are we transferring overall in the bottom one? Sorry, 4. 4 electrons transferred in first equation. 4 electrons transferred in second equation. But how many are transferred in the overall? That is correct. How did you find that?
Well, if one is losing 4 and the other is gaining 4, then
That's one way. That's one way of looking at it. One is losing 4, one is gaining 4. That's obvious there. You can also look even here. You have 2 coppers becoming 2 copper 2 pluses. That means that's a positive 4, which means it had to have spit off 4 electrons somewhere. And look, the charge on this manganese right there is a positive 4, and it went down to a 0. So it must have gained those 4 electrons. So overall, again, 4 electrons were spit off by the copper, 4 were gained by the manganese. So the nice thing about this is, since 4 electrons are transferred in the third equation, we can just add them up. And so this one would be a negative 0.3205 volts, which means it is not spontaneous as written.
Question.
Yep.
Do you not have to multiply the first equation by 2, the E naught by 2?
Oh, good question. Should I multiply my voltage by 2? And the answer is no. Remember, these voltages are intensive properties. They do not depend on the amount. Again, go back to thinking about your battery. No matter if you have a AA, AAA, or D cell battery, those things are going to give you 1.5 volts, no matter how big they are. The bigger they are, the longer they last because they have more metal, they have more electrolyte, they have more of everything. So again, they can go longer, but their voltage is exactly the same because they're just made up of the same metals with the same difference in their activities, doing their thing thermodynamically. I know, it's weird. We spent all this time multiplying, and finally we're like, wait, we don't have to do anything? That's weird. Okay. Last one, then we'll just call it a day. So when we look at the original equation up there, looking at this, this one that was the MnO2 plus 4 H pluses plus 4 electrons going to make manganese and H2O. It is not in the book. But this is where it's cool. Sometimes you get an electrochemical reaction that you either want to do or are seeing, and you want to go ahead and do some predictions, and you say to yourself, well, let's just go get the numbers. And then you go look for that reaction, and it isn't there. What you might find is the following. We have but, you find that there is an MnO2 plus 4 H pluses plus 2 electrons will give you manganese 2 plus and 2 waters. And you find that manganese 2 plus 2 electrons will give you manganese. This is what you find. The E naught for the first one is 1.224 volts. The E naught for the second one is negative 1.185 volts. Now, if you add these up, you get MnO2 plus 4 H pluses plus 4 electrons goes to make manganese and a couple of waters. So the question is, what is that voltage? Well, pro tip, it's up there. I gave it to us. But here again, I want to point out that sometimes you don't always have the equation you want, but you have to build it from somewhere else. And what we're going to see is we're going to have a different number of electrons transferred for each one of these. So since the number of electrons transferred is not all the same, we would have to do that third voltage is N1 E1 plus N2 E2. Might as well do some knots here. All over N3. And so that would be 2 electrons times the 1.224 volts plus the 2 electrons times the negative 1.185 volts, all divided by the 4 electrons that we see in the third reaction. And that is our positive 0.0195 volts. Same as above.
Horace,
Yes.
if you scroll up where you wrote the equation out, I think you forgot to write 2H2O.
Wait, say that again?
Go up again, like a little bit more. Yeah, just like in that equation down there when you said looking at, nope, down. I think you just forgot to put 2H2O
Where?
at the end of,
Oh, 2H2O. Yeah, sorry. Thank you. There we go. Thank you. So this is just to show you that there are going to be times where you may want this information. You may go to the place you think you're going to find it and it's not there. But you will be able to construct it from other equations. Whether people just never studied this one, or whether it was just too difficult, or whether they're like, well, we already have the pieces, why do this? You know, we don't need a reduction table for everything if you can build it from other stuff, because they found that this is self-consistent. If you have the pieces must add up to the whole, and that makes sense because of thermodynamics. You know, if you got two equations that give you two different delta H's, you can figure out that difference. That difference will translate to a voltage. And so you can, in more than one fashion, figure out a way to determine the information you need. So again, when I did this equation up top, and I just said, oh, hey, there's the voltage. Of course, you're sitting there just like I would be like, okay, yeah, you just looked it up. Well, I didn't. I actually looked up two other reactions to figure out what the last one would be. And that's how I actually got that one, because you won't find that one on a reduction table. So that's kind of cool.
I have a question.
Good.
Would you also be able to flip the first equation and change the sign and then?
Yes. So we, at the end of this, we said, look, this is not going to happen, right? So if we were to actually build this whole thing and say, let's go for it, you would find that the copper is not going to react with the manganese 4 oxide, but rather copper ions would react with manganese and start spitting out the other direction. So you could build this the other way and say, I don't want to look at it this way. I want to look at it the other way. And yes, you get a positive 0.32 or 0.3205 volts. So remember, it's not spontaneous as written, it's going backward.
Gotcha.
Oh man. So we'll do that. Oh man, I totally wanted to get, oh, no. I think our brains are full for now. But we will be able to get through everything on Thursday. And so I do want to give you guys something to think about, because we'll take a vote on Thursday. And that is, do we want to have the exam Tuesday so that we can have some extra time to sit in one of these little meetings, kind of like a reviewish session and a Q&A time? Or do we want to have a Q&A time and do the exam on Thursday, but have very, very little, if no time, before the final? So I want you guys to think about that, and we'll talk about it on Thursday. But I'll give you guys the option of a Tuesday or Thursday exam. Keep in mind, if you do Thursday, I'll try to get them graded as fast as I can. All right, any other burning questions before I stop recording?